Hello everyone. Today we are going to study self-phase modulation and cross-phase modulation. The contents of this lecture are introduction, self-phase modulation, cross-phase modulation, and references. So let's start with introduction part. The origin of self-phase modulation and cross-phase modulation lies in ultra-fast third-order susceptibility Chi3. As we have already discussed, Chi3 is a complex quantity which has both real and imaginary parts. The real part of Chi3 leads to self-phase modulation or SPM, cross-phase modulation or XPM, four-wave mixing or FWM. In this particular lecture, we are going to cover self-phase modulation and cross-phase modulation. Non-linearities due to intensity-dependent variations in refractive index are called Kerr effect. So, self-phase modulation and cross-phase modulations are governed by Kerr effect. Let us see Kerr effect in detail. The Kerr effect is the phenomena observed in non-linear optic materials, where the refractive index of material changes in response to an electric field. So, as the electric field changes, we can observe some changes in the refractive index. The refractive index N of many optical materials has a weak dependence on optical intensity I, where optical intensity I is defined as I is equal to power applied divided by effective area. So the refractive index would be N is equal to N naught plus N2 multiplied by intensity I. If we put value of intensity I equal to power divided by effective area, this equation would become N naught plus N2 multiplied by P upon A effective. Here N naught is ordinary refractive index that we usually use, and N2 is non-linear index coefficient. So this non-linearity comes from this term N2. The value of N2 is about 2.6 into 10 raised to the power minus 8 micrometer square per watt for the silica, and it is in between 1.2 to 5.1 multiplied by 10 raised to the power minus 6 micrometers per watt in telluride classes. The nonlinearity in refractive index is known as Kerr nonlinearity, and this Kerr nonlinearity produces a Kerr-induced phase modulation of propagating signals, and this Kerr-induced phase modulation of propagating signal is called Kerr effect. Next topic is self-phase modulation. In single wavelength links, not in WDM system, we are talking about single wavelength links. So in single wavelength links, the Kerr effect gives rise to self-phase modulation. This self-phase modulation converts light power fluctuations in a wave to spurious phase fluctuations in the same wave. So there are some phase fluctuations in the same wave. The magnitude of non-linear effect for SPM is given by gamma is equal to 2 pi by lambda multiplied by N2 upon A effective, where notations have their usual meanings. The frequency shift arising due to self-phase modulation is given by delta phi is equal to d phi by dt, which is equal to gamma that we have calculated over here, multiplied by effective length L effective multiplied by dp by dt, which is nothing but power fluctuation. So we are seeing here that due to power fluctuation, some phase fluctuation is taking place. In a medium having an intensity dependent refractive index, a time varying signal intensity will produce a time varying refractive index that we can understand from this figure. Here we can see that power is increasing. So power is, or I can say that power is fluctuating. Here power is minimum, here power has started increasing, and here power is maximum. Okay, so power is increasing over here, Here it has become maximum. Again, power is reducing, and here again it has become 0. So the leading edge of a pulse will see a positive dn by dt, whereas trailing edge will see a negative dn by dt. As we have already discussed in Kerr effect, that the fluctuating power will give rise to fluctuating refractive index. So we can say that refractive index profile would also be similar to this. When power would be constant, refractive index would also be constant. When power will change, refractive index will also vary. When again power will become constant, refractive index will become constant. Again, when refractive index will change, when power will change, refractive index will also be changing. So on this leading edge of the pulse, the refractive index variation dn by dt would be positive, and on this trailing edge, the refractive index variation dn by dt would be negative. This leads to frequency chirping, in that the rising edge of the pulse shifts towards lower frequencies and trailing edge towards the higher frequencies. So because of this refractive index variation, frequency shift or frequency chirp takes place, and because of this frequency chirp, what happens is that suppose your original signal was placed between a frequency f1 and frequency f2. Then after this chirping will take place, your frequency spread will not remain between f1 and f2, rather it will spread from f1 minus delta, so some point from here, to f2 plus delta, so some point over here. So overall pulse width will spread in the frequency domain, which is called dispersion. So this is how cell phase modulation works. Cross phase modulation. Cross phase modulation appears in WDM systems, and it has similar origin as SPM. So the origin for SPM and XPM are same, but SPM is for single wavelength channels, while XPM or cross phase modulation appears in WDM or multi wavelength channels. The refractive index nonlinearity converts optical intensity fluctuations or power fluctuations in a particular wavelength channel to phase fluctuations in another co-propagating channel. So because of power fluctuation in one channel, phase fluctuations will take place in another co-propagating channel or nearby channel. XPM only appears when two interacting light beams or pulses overlap in space and time. So both these channels should be overlapping in space and time. Then only this XPM effect will take place. For two co-propagating wavelengths, the XPM induced phase shift is given by delta phi is equal to d phi by dt, which is phase change. This is equal to twice of gamma L effective dp by dt. And when multiple wavelengths are propagating in a fiber, the total phase shift for an optical signal with frequency omega I is given by delta phi I is equal to gamma L effective dpi by dt plus twice summation j is not equal to I dpj by dt. Here this first term dpi by dt, it represents self phase modulation, because here we are talking about the same channel phi I pi, and this second term, it represents the cross phase modulation or XPM, because here for channel I we are considering all other wavelengths except j is equal to I. So this is how XPM works in optical fiber channels. Thank you. If you have any doubts or queries, you can post them at discussion forum of www.chetanselwal.com. You can also visit the website for lecture notes. Thank you.